Okay, so here we have four charges arranged in a rectangular shape. -5 coulomb charge A, +3 coulomb charge B, +4 coulomb charge C, and a -2 coulomb charge D, arranged on the corners of this 3x4 meter rectangle. And we could figure out a variety of different things about this, but let's say what we're trying to find is what's the force acting on charge D. So let's say that's our goal here. So that's our goal. What's the force acting on charge D from the other three charges? Which suggests, using the terminology we've been seeing, we'd be treating charge D as the what here? What do we call the charge that's experiencing a force that we care about?
Is it the source charge?
Other way around. The source charge is the charge that we're treating as creating some sort of effect. The charge.
So this would be the. Oh.
Sorry, what was that?
Sorry, I was about to say test charge when I interrupted you.
Yeah, no problem. But yeah, we would call that the test charge. And there's no physical difference between source charge and test charge. It's just charged objects. But usually we tend to think of it in terms of some object that's experiencing a force from other stuff. We call that thing that's experiencing the force the test object or test charge. And then all the other stuff that's creating the effect on it, we call these source charge or source charges. So in this context, we're treating QA, QB, and QC as the source charges, and QD as the test charge or test object. Again, no physical difference between those. It's just a matter of perspective. What we're treating as creating some sort of effect and what we're treating as feeling the force from that effect. Because in reality, it's just four objects that are all exerting forces on each other. But if we just care about the force on object D, we're going to treat that as the test object. Which means we're effectively going to just be treating charge D as an empty point in space for now. For the test charge, what we typically do is use these source charges to create the idea of an electric field. So the source charges create an electric field in the space around them. And then the electric field creates a force on the test object. So we typically do this in two steps. We look at this in terms of the source charge creating an electric field. And then separately, we also look at it in terms of the electric field creating a force on the test object. Any questions on that general idea so far? So let's start with the idea of these source charges creating an electric field. That means what we're going to do to start with is we're going to ignore the test object entirely. We're essentially going to instead of treating D as a charge, we're just going to treat D as an empty point in space. So ignoring charge D for now, we're just going to look at location D, an empty point in space. And what we care about is what's the electric field at that location caused by everything else. So if we take a look at this one step at a time, we can say each one of these three charges, A, B, and C, is creating an electric field at location D in some way. For example, let's say we take a look at charge C. Charge C is going to create an electric field at location D in which direction?
Would it be like out, like all direction?
Yeah, if we look at just the space around charge C, C is a positive charge, so it's going to create electric field outwards, away from itself in all directions. But we don't care about all those directions. We don't care about all the locations around charge C. We only care about location D. So at location D, which direction is outwards from charge C? Yeah, to the east or to the right, whatever you want to call that direction, the positive X direction. So the electric field caused by charge C at location D is to the east or to the right. So let's call that E sub C. The electric field caused by charge C, or we would say the electric field contribution, because this isn't the actual electric field at D. This is just the contribution caused by charge C to that electric field. So charge C contributes some amount of electric field at location D. And can we calculate how strong that contribution is? We know it's in the positive X direction. How would we figure out how strong it is?
We use like KD over R.
K times what was it?
K times D over R squared.
And what's the D there?
Or KQ, sorry.
Yeah, K times that charge, in this case, charge C, divided by R, the distance squared. And in general, that works anytime you've got a single point source charge. For a single point source charge, in the sense that charge C is so compact that we can, I mean, even if it's not truly a single point, presumably it's a sphere or something, but it's so small compared to the other distances involved, we can treat it as a single point. Like if charge C is a ball 1 centimeter across, 1 centimeter is pretty small compared to the 4 meter distance. So we can treat charge C as just a single dot. And in general, for a single source charge that's small enough to be treated as a single point, we can say the magnitude of the electric field is K times the source charge divided by R squared. And we should really think of that as K times absolute value of the source charge. Because the sign matters for direction, but doesn't matter for the magnitude. So K, which is a universal electrical constant, and has a value, but we can just leave it as K for now and fill in the value at the very end, times 4 coulombs divided by the distance, 4 meters squared. So that'll be K times 4 coulombs divided by 4 meters squared, which reduces to what? What is 4 over 4 squared?
1 over
1 over 4.
Right. So we can simplify this to just K over 4. And we still have units of coulombs and meters squared. So coulombs per meter squared would be the units. So that's the electric field contribution caused by charge C at location D. K over 4 coulombs per meter squared. Any questions on that so far? And what about charge B? Charge B is also positive, so that's going to create electric field at D in which direction? Yeah, directly to the south or down, whatever you want to call that. And would you expect that to be stronger or weaker than the contribution from C, or can we tell yet? We've got a weaker charge, so what does that suggest about the electric field? In general, would you expect a weaker charge to create a stronger or weaker electric field? Yeah, the charge alone suggests a weaker electric field. It's also closer, 3 meters away instead of 4 meters away. Would closer suggest a stronger or weaker electric field?
stronger.
Yeah. So the weaker charge suggests a weaker electric field. The closer distance suggests a stronger electric field. So we can't really tell yet. Maybe it's weaker, maybe it's stronger, depending on how those balance out. But we can tell by running the calculation. electric field caused by B is going to be K times the absolute value of charge, 3 coulombs, divided by the distance, 3 meters squared. So what does that reduce to?
One-third.
Yeah, 1/3 of K. So K over 3 coulombs per meter squared. And 1/3 is a little bit more than 1/4, so it looks like B is creating a slightly stronger effect. And that'll be directly to the south. So I'll draw a slightly larger arrow directly to the south. So that's the electric field caused by B. Any questions on those so far? And what about for charge A? That's a negative charge. So which direction is going to be the electric field at D caused by A? Southeast? Except this is a negative charge, so what does that suggest? In general, which direction should we expect the electric field caused by a negative charge to be pointing?
Like inwards? Like towards?
Yeah, exactly. Electric field caused by a negative source charge is going to be pointing inwards towards that charge. So yeah, that'll be northwest, not directly northwest, but approximately northwest-ish, a little more west than north on this diagonal here. So pointing straight towards charge A. And again, we can calculate the strength using the same formula. Electric field caused by A is going to be K times 5 coulombs. And again, we're treating this as absolute value because we're just looking for magnitude here. Divided by, and what's the distance? How far is it from charge A to location D?
5.
Yeah. And how do we figure that out?
3, 4, 5 triangle.
So the 3, 4, 5 right triangle. Or if you don't remember that, you can always use Pythagorean theorem, 3 squared plus 4 squared, and take the square root. So we know we got a 5 meter distance, which means we can just take K times 5 coulombs divided by 5 meters squared. 5 over 5 squared reduces to 1/5, so that'll be K over 5 coulombs per square meter. So we now know at least all of the electric field contributions caused by each of these source charges. Any questions on those contributions so far? I guess that should actually be smaller than the others. And then what do we do with those? If we've got a bunch of vectors, a bunch of electric field contributions all acting at one location, what do we do with those to find the actual electric field at that location?
You have to do vector math addition.
Yeah, the actual electric field is just the sum, the superposition of all 3 of these contributions. In general, if you've got, they're the whole idea of superposition, whether it's electric fields or waves or anything else. If you've got several sources trying to create some sort of effect at the same location at the same time, you can typically add together those attempts at causing some sort of effect. So we can just add EA plus EB plus EC. We're just going to add those together to get the total. But since they're vectors rather than scalars, we need to think of them in terms of their components, since that's generally the most useful way of adding vectors. So writing these in terms of components, how would we split, or how would we write these in terms of their components, the X and Y components? Which ones would probably be easiest to write in terms of their components to start with?
C and B.
Yeah, C and B are pretty straightforward because those are in these nice, neat orthogonal directions. B, for instance, is purely in the y direction, negative y direction. So we can write that as just 0, comma, negative k over 3. And these are all going to have units of coulombs per meter squared. So I'm just going to leave off the coulombs per meter squared for now. And then C is k over 4 in the positive x direction. So k over 4, 0. And what about the contribution from A? How could we split that into components?
Would we use trig? So one of the components would be the magnitude of A times cosine of the angle. And then the other one, it would be the magnitude of A times sine of the angle.
Yeah, we could certainly use that. But we don't have the angle yet. Is there any way we could find that angle? Let's say the angle this makes with horizontal.
Yeah. It would be 45 degrees because 3-4-5 triangle, right?
3-4-5 triangle is not 45 degrees though. 45 degrees would make it so that the sides are the same length. But
well,
we can,
if you know it's a right angle, and then both the other angles have to be the same.
The other angles would only be the same if the two sides were the same. This was like 4 and 4. If the sides were the same length, then these would both be the same angle. But since these sides are not the same length, 3 and 4, that means these two angles don't match either.
Got it.
Although keep in mind, these two sides are not 3 and 4. These are some unknown amount of newtons per coulomb. But if we do draw out a 3-4-5 triangle, specifically the one involving distances, 3 meters, 4 meters, and 5 meters. I've just drawn out a triangle of distances and a triangle of electric field contribution. What do those triangles have in common? What's the same about them?
They're both right triangles.
They're both right triangles. So the right angle matches up. Right angle, right angle. Do they share any other angles?
The one on the bottom right?
Yeah, this one on the bottom right, the angle at point D, that's the same angle on both of them because it's the same point. They both have, I can actually put that in there. This interface makes it very difficult to move small things. Yeah, this angle is shared by both of those triangles. And if the triangles have two angles matching up, then by the angle sum formula that they have to add up to 180, the other angle also has to match up. So this angle in the small triangle has to match this angle in the large triangle as well. And if all the angles match, what does that tell us about these two triangles?
They're like proportional to each other.
Yeah, triangles that have the same angles are proportional to each other because they are similar triangles. So we don't actually even need to know what the angle is. We don't need to use sine and cosine directly with the angle. We can just set up ratios of sides. We can say, for example, we can say that the ratio of, let's call this EAX and EAY. So EAX, EAY. We could set up ratios of, like, let's say, for instance, we wanted to define EAX. We know EA, the hypotenuse, is k over 5. So we could say the ratio of EAX over the hypotenuse, EA, that has to match the corresponding ratio in the larger distance triangle. The same longer side, the x component in this case, which is 4 meters, over the hypotenuse, which is 5 meters. So long side over hypotenuse of the electric field triangle has to match long side over hypotenuse for the distance triangle, 4 meters over 5 meters. In other words, EAX is going to have to be EA times 4/5. So the X component is going to be exactly 4/5 of the hypotenuse. We know the hypotenuse is K over 5. So K over 5 times 4/5 is going to be 4K over 25. So that's the X component. Or rather, since it's to the left, that'll be negative 4K over 25. Any questions on that X component so far? And then what about the Y component? How would we find that? What ratio could we set up that would involve the Y component? If we say EAY over what? Yeah, I think 3 should work. Not 3/5 though, but 3, let's say EAY over the hypotenuse, same idea as we had before. The Y component over the hypotenuse has to equal the short leg over the hypotenuse of the other triangle. So that'll be 3 meters over 5 meters. So that ratio does work out to 3 over 5. Multiply both sides by EA, and we find that the Y component is 3/5 of the magnitude. And we know that the magnitude is K over 5. So 3/5 times K over 5 would be 3K over 25. And since that's upwards or northwards, that'll be positive 3K over 25. So we now have the X and Y components. No sine or cosine directly needed. We are kind of doing sine and cosine indirectly, since X component over hypotenuse is sine of the angle, cosine of the angle, adjacent over hypotenuse. So this ratio is cosine of the angle, but instead of typing cosine of a known angle into the calculator, we're getting cosine of that angle by using another triangle whose distances we know. 4 meters over 5 meters is adjacent over hypotenuse. So this is the cosine of the angle. We're just jumping directly to that ratio from another triangle rather than finding the angle first. So that's often very useful. Watch for similar triangles and set up proportions whenever you can. This is often a very useful way of fairly quickly getting a ratio of distances and solving for an unknown value without even needing to know what the angle is numerically. Any other questions on the geometry behind that so far? All right, then now that we know the components, let me tidy this up a little bit. Let's fill that in. We know EA is X component, negative 4K over 25, Y component, positive 3K over 25. And then we can add those together. E net at location D, we can just add up negative 4K over 25 plus 0 plus K over 4. And what's a common denominator there between 25 and 4? Yeah, they're both factors of 100. So negative 4K over 25 would become negative 16K over 100 plus another 25K over 100. So 16 plus 25, or negative 16 plus 25 would be 9. So we end up with 9K over 100. And then 25 and 3, what's the common denominator there? Yeah, they're both factors of 75. 25, we'd have to multiply by 3, so 9K over 75 minus 25K over 75. So 9 minus 25 would be negative 16. So negative 16K over 100, or over 75. So there's the components of the total electric field at location D. 9K over 100 to the right, 16K over 75 downwards. Any questions on that so far? So now that we know that, let's write in what we know of that, or let's draw that in geometrically as well. Tidying this up a little bit. If we draw out the total electric field at that location, that is 9K over 100 to the right and 16K over 75 downwards. So I guess mostly downwards, a little bit to the right. Something like that. So that's the actual electric field at location B. Any questions on that so far? Oh, and of course, that will also have units attached to it of coulombs per meter squared. We can also even factor out the K and say there's 9/100ths, comma, negative 16/75 K coulombs per meter squared. So there's the total electric field. And what could we now do with that? We've got the components. What might be a more useful way to write that, though? We can find the force, although before we do that, what if we wanted to know what would be another way we could write the electric field other than X component and Y component?
Could you draw it? Like draw a vector?
Well, we've drawn the vector, 9/100ths in one direction, negative 16/75 in the other direction. But what if we wanted to know how strong the electric field actually is? How could we convert X and Y components into an actual magnitude of that electric field? How do you typically find the magnitude of a vector?
Is that where we would do the Pythagorean theorem?
Yeah, because the components are the how far in the X direction and how far in the Y direction. What we care about is the actual size of this vector, which is the hypotenuse here. So if we label these as X is 9/100ths and Y is negative 16/75, the Pythagorean theorem will use those two legs to find the hypotenuse. So 9/100ths squared plus 16/75 squared, we can ignore the negative because it's squared anyway, then take the square root of that, and that'll tell us the magnitude here. So let's try that out. Calculator. We've got square root of 9/100ths squared plus 16/75 squared. So I'm getting about 0.23 K. So that's the magnitude. Magnitude of the electric field at this location is about 0.23 K coulombs per meter squared. And what about direction? If we want to know the actual direction it's pointing in terms of an angle, how would we find this angle that it makes with the x-axis? Yeah, tangent of that angle should be opposite over adjacent. So negative 16/75 over 9/100. So tangent of theta, get theta here. Theta. There it is. So tangent of this angle is going to be opposite over adjacent. And then if we just take the inverse tangent of that ratio, so inverse tangent of negative 16 over 75 divided by 9 over 100, I'm getting about negative 67 degrees. So that is, in other words, 67 degrees below the axis. So we now have magnitude and direction. We know that the magnitude of the electric field is 0.23 K coulombs per meter squared in a direction of 67 degrees below the axis. Any questions on that so far? Now that we know how strong the electric field is in terms of K, which we could fill in later if we need to, and also in terms of the direction. So now that we know the electric field in terms of magnitude and direction, let's say we want to find the actual force on this test charge, because we've been ignoring the test charge. We've just been ignoring the test charge and looking at the source charges creating an electric field. But now that we've got that electric field, we can investigate the electric field creating a force on the test object. So let's actually bring back that test object. We've been ignoring charge D for now, but now let's actually bring that in. We now know that is charge D is negative 2 coulombs. And first of all, without even worrying about magnitude at all, if the charge is negative 2 coulombs, what does that tell us about the direction of the force on charge D? Outwards from what? Or what do you mean by outwards or inwards? Not the electric field caused by charge D. We know the electric field caused by everything else. If we want to know the force that charge D experiences because of that electric field, what do we know about the force on a negative test charge as compared to the electric field at that location? Or how is electric field and force related in the first place? If you know the electric field, how do you determine the force on the test object? Do you have any equations or other relationships describing how the force and the electric field are related to each other?
Are they negative derivatives? Oh.
I think you're thinking of the voltage. The electric field is the negative derivative of voltage. But yeah, force is charge times the electric field. The force acting on the test object is the test charge times the electric field at that location. So this relationship describes how the electric field is related to the force on the test object. The force on the test object, which we should think of as a vector, the force on the test object is equal to the charge of the test object times the electric field at that location caused by whatever other source charges we're dealing with. We now know the electric field at this location, which means we can now completely ignore the test objects. This is one of the big advantages of finding the electric field. Now that we know the electric field caused by charges A, B, and C, we can now ignore charges A, B, and C entirely. We no longer need to worry about those. Everything we need to know about those is summed up by the electric field they cause. So we can just say whatever those charges were, it doesn't matter. What matters is they create an electric field with this magnitude and this direction. Now that we know the electric field, we can just multiply that total electric field by charge D, the test charge, and that'll tell us the force acting on charge D. So for magnitude, we're just multiplying the 2 coulomb amount of charge times the electric field, 0.23 K coulombs per meter squared. But what happens to direction? If you've got an electric field vector, or any vector really, if you've got a vector pointing in a specific direction and you multiply by a negative scalar, what happens to the direction of the result? Yeah, a negative multiplier flips the direction of the vector. In general, if you multiply by a positive scalar, the direction doesn't change. If you multiply by a negative scalar, you get a vector in the exact opposite direction. So the force acting on D, force on charge D, is going to be in this direction. And how would we write that direction in terms of angle? What would that angle be? Or how would we calculate that angle? That is, how would we find numerically the angle that's exactly opposite to the angle negative 67 degrees? Yeah, we can just add 180 degrees to the negative 67 degrees we've already got, because flipping around exactly half a rotation is 180 degrees. So we can take the negative 67 degrees we've already got, add 180 degrees, and get positive 113 degrees. So that means the force acting on charge D is at an angle of 113 degrees counterclockwise from the positive x-axis. Or you could deduct 90 and say it's 23 degrees west of north. So we could describe this angle as 23 degrees west of north. That might be probably the most convenient way to describe that. So the force acting on charge D is at a direction of 23 degrees west of north, or 113 degrees from the positive x-axis. And in terms of the actual strength, the magnitude of this force, we can just take the electric field we've already got, 0.23 K coulombs per meter squared, and multiply by the magnitude of the charge, 2 coulombs. So 2 coulombs times 0.23 K coulombs per meter squared equals 2 times 0.23, that'll be 0.46 K. And then what happens to the units there? If we've got coulombs per meter squared, we multiply by coulombs, what's left? We're multiplying coulombs times coulombs though, so those don't cancel out. Yeah, we'd end up with coulombs squared per meter squared. So 0.46 times the universal electrical constant K and units coulomb squared per meter squared. And the coulomb squared and meter squared are really just to get the units to work out, because K itself is measured in newtons meters squared over coulomb squared. So we should end up with just newtons. And at this point, we could also fill in the value of K. Anyone happen to know what the value of K is? I think is it about 10 to the 10th or 9 times 10 to the 9th, I think. K is approximately 9 times 10 to the 9th Newton meters squared per coulomb squared. So if we fill that in, 0.46K means 0.46 times that value. Yeah, 8.99, or we can probably round that off to about 9. So 0.46 times 9 times 10 to the 9th. 0.46 times 9 times 10 to the 9th is about 414, and then a whole bunch of zeros. 3, so about 4.14 billion, I think. Yeah, about 4.14 billion. So that would be 4.14 giganewtons, which is an enormous amount of force. And ultimately, this is an enormous amount of force because 5 coulombs and 3 coulombs and 4 coulombs and 2 coulombs, these are very large amounts of charge. We wouldn't really expect that enormous an amount of charge to be dealing with that much charge in a real world example. But this is what we would get for the force if we had this much charge. Any questions on that? Or any other questions on dealing with electric fields and vectors in general? And by the way, the order is kind of flexible here. In this example, we converted the XY components into the XY components of the electric field into magnitude and direction of the electric field, and then multiplied by test charge to find the magnitude and direction of the force. You could also do that in the other order. You could find the XY components of the electric field and multiply both X component and Y component by the charge, -2 coulombs, to get the X and Y components of the force, and then convert that to magnitude and direction. So you could really convert to magnitude and direction either before you multiply by the test charge or after you multiply by the test charge. You should get the same result. But the important relationship there is that the force on the test charge is the electric field at that location, caused by all the source charges, times the test charge. So that's really 2 big tasks to do here. I mean, even apart from all of the vector arithmetic stuff, use the source charges to find the electric field at some location. And then separately use the electric field you just found to find the force on the test object at that location. But notice that you don't really need to have the source charge and the test object both involved at your calculations at the same time. You separately calculate the source charge creating the electric field. Then once you know that, you can ignore the source charges and say the electric field itself creates a force on the test object. And again, what's really happening is all these forces are exerting forces on, all these charges are exerting forces on each other. But adding this extra step of the electric field as the thing created by the source charges and also the thing creating a force on the test object makes it so that we don't have to worry about the source charges anymore as soon as we find the electric field. Once you've got the electric field, you can ignore the source charges entirely. Any other questions on that? All right, and if you want to get some more practice on this, try this from a different perspective. Treat, let's say, A, B, and D as the source charges, figure out the electric field they create at location C, and then use that to figure out the force that charge object C feels as a test object from everything else. So try that out, get some more practice, and I will see you next time.
Thank you.
You're welcome.